Question 7 looks at a real-life example of how an industrial process has been improved to make it more efficient in terms of atom economy. So the ibuprofen story is sort of recognised as one of the kind of triumphs of green chemistry. And, you know, the drug companies probably switched their production method because it cost them less, but nevertheless it's good that it had this side effect that it produced a process which is much less wasteful in terms of the amount of raw material that ends up getting turned into stuff that gets thrown down the drain. So it tells us that pre-1990 we had a process that only had 40% atom economy. So what that means is that the mass of product per year, which is 3,000 tons, is 40% of the mass of raw materials used. Okay, so that's putting in words what the atom economy means. That 3,000 tons of product is produced, and that's only 40% of the mass of raw materials used. So that means that we can calculate the actual mass of raw materials is equal to 3,000 tons. And then if you divide that by 40, remember that's 40% of the total, so if you divide that by 40, that gives you 1% of the total, and then if you multiply by 100, that gives you 100% of the total mass. Okay, so that's a way of rationalising the fact that to scale up from 40% to 100%, you multiply by 100 over 40, which gives you 7,500 tons. So that's the mass of raw material used in a year to produce your ibuprofen. Now if we do the same calculation post 1990, we're going to get that that's equal to still 3,000 tons, because our consumption of ibuprofen we're assuming is roughly the same, but this time it's 77% efficient in terms of atom economy. So when we scale up, it'll only be times 100 over 77, and if we do that calculation, that comes to 3,896 tons, or let's say 3,900 tons. So you can see much less mass of raw material per year going in, because more of it actually ends up as ibuprofen. And so just by subtraction we can get that the mass of raw material saved by the new process is just 7,500 minus 3,900, which is 3,600 tons per year. Okay, question 8 is asking us about this quite important reaction, which is called steam reforming of methane, and that's the reaction. So methane plus steam gives you this equilibrium reaction. Okay, so it's a reversible reaction to give you carbon monoxide and hydrogen. So what that means is that you wouldn't expect all of this methane and hydrogen actually to get converted into carbon monoxide and hydrogen, because although that forward reaction can happen, the back reaction can also happen, and so you're going to get a balance between them, and you're going to get an equilibrium when some of this will have been converted but not all of it, because the rates of the forward and back reactions become balanced. And the question is saying, okay, what effect is this going to have on these parameters we've been talking about, percentage yield and atom economy? Well, in terms of percentage yield, you can see that it suggests that the percentage yield will be lower than than 100%. In other words, the percentage yield will decrease because not all of it is going to get converted into product. So 100% yield based on the amount of methane would mean that all of the methane would have to get converted into carbon monoxide, and that's not going to happen because of the reversibility. So the percentage yield is going to be lower than 100%. Atom economy, on the other hand, is just calculated from the equation. It doesn't really take account of this. It just sort of says, right, if these are the products, you plug the numbers into the recipe, and the fact that this is reversible doesn't change anything. It really, though, is clear that that's not an appropriate thing to do. It just means that atom economy is a bit of a sort of meaningless concept when you have a reversible reaction like that. Okay, in part C, we've got to figure out how much methane we need to produce 100 dm cubed of hydrogen measured under those conditions. So that's obviously going to depend on taking account of the 44% yield, but before we can do that, we need to know how many moles this is. So our starting point is to recognise that if we're given a volume of gas, there are two approaches to calculating moles. If it was at room temperature and pressure, we could use the trick with 24 dm cubed, but it's not. It's at 100 degrees C. So we have to use the full ideal gas equation, which is that PV equals nRT. So you write that down and then immediately rearrange it because we want to know what the number of moles is. So we get that N is equal to PV divided by RT. And we plug the numbers in. So P is the pressure in pascals. So if it's 100 kilopascals, that's 100,000 pascals times the volume. And the volume is meters cubed, is the slightly strange unit that we use for volume when we use this equation. So 100 dm cubed, remember there are 1,000 dm cubed in a cubic meter. So 100 dm cubed is 0.1 cubic meter divided by R, which comes from your data sheet, is 8.314, and the temperature, remember, has to be in Kelvin. So 100 degrees C, we add 273 to that and get 373, and those are the numbers. So we plug those numbers in and we get 3.226 moles. So that's the number of moles of hydrogen that we need to produce. So the next step is to calculate how many moles of methane we would therefore need by taking account of the percentage yield. So we write down the definition. Percentage yield is actual moles over theoretical moles times 100. So we know what the percentage yield is because it tells us it's 44%, and we know what the actual moles we want to produce are because that's what we've just worked out. So what we need to calculate are the theoretical moles, because from this equation we know that theoretically for each 3 moles of hydrogen you need 1 mole of methane. So if we can work out what the theoretical moles of hydrogen will be, we can back calculate what the moles of methane would need to be. So that's going to be the strategy. So first we need to rearrange this equation to get what the theoretical moles will be. And so you can see that if we slide theoretical moles up onto that side and then we slide percentage yield down over to there, we can rearrange that to get theoretical moles is equal to actual moles divided by percentage yield times 100, which is 3.226 divided by 44 times 100. And that works out as 7.332 moles. So that's our theoretical moles of hydrogen. But as we said, the equation tells us that you get 3 moles of hydrogen from each mole of methane, theoretically. So if we want the moles of methane, we have to divide by 3. Okay, so that means that the moles of methane needed is the theoretical moles of hydrogen divided by 3, which is 7.332 over 3, which works out as 2.444 moles of methane, and then we can just turn that into a mass. Okay, so the mass is moles times mR, which is 2.444 times 16, which is 39.1 grams is the final answer. Okay, so quite a lot of working out there, but the principles all just come down to learning that equation, rearranging it, and just being careful that theoretical moles doesn't always just equal moles of starting material. It does if you've got equal moles on both sides of the equation, but that wasn't the case here, so make sure you understand where that factor of 3 came from.